Hello, my CFA friends. How are you, my friends? So we're going to be talking about hypothesis testing in this reading, so let's get started. Before anything, I want to talk a little bit about the terminology, right? So we've got a list of words, buzzwords that we need to plow through and understand. And after we do that, we're going to look at some hypothesis testing examples. Okay, so in hypothesis testing, we obviously have to set up a hypothesis that we want to test and potentially reject. So the status quo hypothesis is known as the null hypothesis. We're going to be denoting it as H0. And the null hypothesis is typically the hypothesis that will contain the equal sign. So for example, it might say that the mean is equal to 0. I'm probably hoping to discover that the true mean is different from 0. Now, different means that it is either greater than 0 or less than 0. So as my alternative hypothesis, denoted as HA, I might have something like mu is not equal to 0, right? So this would be an example of what's known as a two-tailed test, right? Because if I were to reject the null, I would be rejecting the null either if the mean is greater than 0 or if the mean is less than 0, right? So this is the first type of test we may have to perform, which is a two-tailed test. The second type of test that we may have to perform is a one-tailed test, one tail, right? So in a one-tailed test, we're going to be using the crocodile sign. So we might say that mu is less than or equal to 0 as our null hypothesis. Notice again how the null must contain the equal sign, even though it also contains the less than sign. And our alternative hypothesis might say mu is greater than 0. So in this case, I will only reject the null hypothesis if I end up in the right tail of the distribution. So just in terms of basically visualizing that, let's actually first visualize this example. So I've got the distro, right? I've got the distro. And let's say it's a kind of normal looking distro. And I will obviously have two tails. So I'm going to have a tail here and I'm going to have a tail here. And there'll be a certain probabilities in this tail. Now, these probabilities are known as the significance level. And the significance level is denoted as alpha. And alpha is sometimes expressed as 1 minus confidence level, right? I'm giving you quite a lot of stuff here, my friends. So if I said I'm performing a test at the 5% significance level, that's the same as saying I'm performing a test at the 95% confidence level, right? Because 1 minus 95 is going to give us 5%. So let's say I was performing a two-tailed test. I'm performing a two-tailed test at the 5% significance level. Well, I'm gonna have to split that 5% probability across two tails. So this left tail will have 2.5%, and this right tail will also have 2.5%. And these tails, these probabilities, will then determine my left critical value, which is negative critical value typically, if we're using the Z or the T, and the positive critical value is to the right, but they are symmetrical, right? And they're going to be determined by the significance or by the confidence. Now, if on the other hand, I were performing a one-tail test. Now let's have another distro here. Let's have another distro here. Okay, so if it's a one-tail test, then perhaps I only consider the tail to the right. In this case, the alternative tells me which tail I'm interested in. So I'm interested in the tail to the right. But once again, I am performing a test, let's say at the 5% significance level or the 95% confidence level. And that is telling me that now the entire 5% is in this tail, right? And therefore that's going to affect my critical value. Okay. So then in statistics, sometimes we're going to make mistakes, and these mistakes are known as type 1 error and type 2 error. Let's go to the Word document and define those things. Okay, so what is a type 1 error? When the null hypothesis is true, but we incorrectly reject it, right? Or this is also known in statistics as a false positive, right? We have a false positive result, okay? So to give you an example, perhaps our null may be that a person is innocent until proven guilty. Okay, that is our null. Null is person is innocent. However, let's also assume that the person is indeed innocent. However, the courts incorrectly convict the person, right? So assume the person is indeed innocent. However, the courts incorrectly convict the person. So that is a false positive because our null is the person's innocent. Then the person was indeed innocent, but the courts incorrectly convicted him. Okay, so that's a type 1 error. The probability of making a type 1 error is equal to the significance of the test, i.e. the alpha. Now, and we can easily see that by observing that we can only reject the null if we are somewhere in the rejection tail, right? And what was the probability of the rejection tail? Well, that was 5%. That was our alpha or significance of the test. Okay, then we've got a type 2 error. So back to the Word document here. Okay, so type 2 error. Okay, so here what we're going to say is when the null hypothesis is actually false, we fail to reject it. So there's a little bit of a double negative here. The null hypothesis was false and we failed to reject it. So statistically speaking, that'll be known as a false negative. That's the lingo. Our null, remember, was that the person is innocent until proven guilty. However, assume that the person is actually guilty of a crime. However, the courts acquit him. The courts acquit him. So he doesn't go to jail. So the courts incorrectly, that's right, that incorrectly fail to convict him. Now that, my friends, is a type 2 error. The probability of making a type 2 error is denoted as beta. We denoted already the probability of making a type 1 error as alpha, so it is only logical that the probability of making a type 2 error is going to be denoted as beta. The next definition here is the power of the test. So the power of the test is equal to 1 minus the probability of making a type 2 error. I.e., It is the probability of correctly rejecting a false null hypothesis. So in our case, that means the probability of correctly convicting a guilty person. So that's the probability of the power of the test. So that would be mathematically denoted as 1 minus beta, right? Because remember, beta was the probability of making a type 2 error. And then lastly, we need to talk about p-values. So again, let's define p-values for you, my friends. So p-value is the smallest level of significance at which the null hypothesis may be rejected. Okay, so the smallest level of significance at which the null hypothesis may be rejected. I like to think of the p-value as the probability to the right of the computed value when you actually look at the distro. And let me explain that for you on the whiteboard. So if I actually had the distro, and let's say that was my critical value, just for simplicity, we will just do it as a one tail. So this probability here is, of course, the alpha. The probability in the tail is the alpha. Whereas if I then have a computed value here, that is my computed value, computed stat, the probability to the right of that computed stat, that is the p-value. Okay, so there's a way to actually use these p-values. They're very, very useful. Now, obviously, I'm going to go through the examples of hypothesis testing in a minute. We're going to actually calculate this computed statistics, and we're going to make decisions based on that. But what I want you to see right now is that this computed stat does lie into the rejection tail, and therefore we should be rejecting our null hypothesis. Remember, our null hypothesis is somewhere here, H0. That is our null hypothesis. We lie quite far away from it, and therefore we are going to reject the null hypothesis. We have a computed stat that does lie in the rejection tail, but we can use these p-values to reject the null hypothesis without having to compute the computed statistic. And so let me explain what I mean by that. What you need to remember, and this is, I think, the key point that you need to remember for your exam, is that you can reject the null hypothesis if the provided p-value, so that's going to be provided, you're never going to have to compute this, if the provided p-value is lower than the significance level. Okay, and this is really the key thing to remember. If your p-value is lower than the significance level, you can reject the null hypothesis quite happily without having to perform any additional statistical tests. Okay, so I believe that's covered everything on this slide. I hope that was clear. But now let us move to the test of a single mean. Okay, so this is gonna be a t-test. It's gonna be a t-test, and the formula for this t-test is going to be the sample mean x bar, take away the hypothesized mean mu, divided by the sample standard deviation, divide square root n. So here effectively our denominator is the standard error. Okay, so let's read our question. A fund has achieved a mean monthly return of 2.5% over the past 12 years with a sample standard deviation of 4.2%. So there's our x bar, There is our S. However, the fund was expected to earn a monthly return of 2%. That is my mu. So that is my population parameter. That is the assumed population parameter over the same period. There's the hypothesis that the monthly return is different from 2%. The word different, of course, does imply that we are going to be looking at a two-tailed test. So my null hypothesis here is going to be that mu is equal to 2. And my alternative hypothesis is going to be that mu is different from 2. You can see here that I'm definitely going to be doing a two-tailed test. So this here is referred to as the computed statistic, which in this case, as you can see, is a t statistic. So I'm going to have to take the x bar, which is 2.5. I'm going to have to subtract the hypothesis mean of 2. And then I'm going to have to divide by the sample standard deviation divided by the square root of the sample size. Now, do be careful here. We have 2 years worth of data, but it's all expressed as monthly returns. So it's actually 2 years of monthly data or 24 observations. So I'm going to have to divide here by the square root of 24. Okay, so go ahead and do this computation and tell me what you're going to get. What you're going to get is spot 583, and that represents our computed test statistic, which we're going to have to now compare to our critical test statistic. So what is our critical t here? I'm going to show you how you can get this on Excel. Okay, so here we are in Excel, and we need a critical t. So what we could do here is we could use the t.inv, the inverse of the t. And we are performing a test at the 5% significance. So I could get the left tail by putting half of that 5% as my probability. So in this case, it's going to be 2.5% in the left tail. And the degrees of freedom for this test are going to be n-1. Okay, very, very important when we're doing this t-test, the degrees of freedom n-1. So our sample size was 24. We're going to lose 1 degree of freedom. So our degrees of freedom are going to be 23 here. And if I close the bracket, I can see that my critical value to the left is minus 2.07. That's my critical value to the left. If I want the critical value to the right, I can simply write this as 97.5. So essentially, I'm going to want to have 97.5% in the left portion of my distro, and that will tell me what the critical value to the right is. And of course, I'm going to get the same value, which is 2.07. Okay, we're gonna draw that in a minute, so you're gonna see. But the critical value is plus minus 2.07. Okay, whereas the computed value is 0.583. So if we just went on to the whiteboard again and just draw our lovely distro. Now remember that T-distro is a symmetrical distro, but it is a leptokurtic distro, meaning that it does have fatter tails compared to the normal. Okay, so here on the right, the value was, let's have a look, it was 2.07, 2.07 plus the value on the right is negative 2.07. I have rejection tails, both left and right. But now remember that the null is right there, bang in the middle at 0. But our computed statistic was 0.583, 0.583. So that must be somewhere here, right? 0.583. So can you see that this is actually fairly close to the null, and certainly it is not in any of the rejection tails. Okay, so if it isn't in a rejection tail, then surprise, surprise, we are not going to reject. We're going to fail to reject. Or more generally, if we go back to our word, we could say reject the null if the computed test statistic is in a rejection tail. Okay, what that actually means is that the computed statistic is either greater than the upper critical value or lower than the lower critical value. Okay? So either higher than the upper critical value, that means we're in the right rejection tail, or it is lower, or it is smaller compared to the lower critical value. Okay? I hope that's clear. So, to cut the long story short, what is the answer here? Our null hypothesis is that the mean was 2%. Yes, we did get a sample that was above 2%. We got a sample mean of 2.5%, but statistically speaking, this was not significantly different from 2%. So we failed to reject our null hypothesis that the mean monthly return of this fund was 2%. Okay, but we can also build a confidence interval around the point estimate. The point estimate is the X bar. It's the sample mean. So in our case, we will take the sample mean plus or minus the critical value times the standard error. That is the formula. Now, of course, you know that the standard error can also be written as the sample standard deviation divided by the square root of n. So we are just going to build a confidence interval here around the sample mean. So I have 2.5, which was my sample mean. Then I have the critical value, which we said was 2.07, rounded to 2 decimal places. Then I had the sample standard deviation at 4.2, and I had the square root of the sample size at 24 months. Okay, go ahead and calculate the upper and lower values. And the answers are 4.27 and spot 73. We are 95% confident that the true population mean lies somewhere between 0.73 and 427. And notice that this confidence interval contains the null hypothesis, which was 2%. And so that also shows us that we're going to fail to reject the null hypothesis, that the mean was equal to 2, right? So the mean is basically equal to 2. So the next test that you need to be able to perform is test of difference between means. So difference in means. So there are actually a couple of tests. One is known as the difference in means test. The other one is known as the mean difference test. So there's a bit of game of words here. Difference in means is going to assume that the samples are independent, and it may assume that the standard deviations are the same or different. If you assume that they are the same, then you use what's known as the pooled estimator of the sample variances. Think of this as some sort of weighted average of the individual sample variances. But the key point here is the difference in means test assumes independence, whereas the mean difference test, which is also known as the paired comparison test, is going to assume dependence. So the samples here are dependent, And in both cases, these tests do continue to be t-tests. Now, I've made a conscious choice here not to go through a numerical example on that, simply because I find them a little bit too tedious for a 1.5-minute question. This does not obviously mean that there is zero chance of you getting that on exam day. I don't know, but I'm not going to be covering this here. If you are very worried about it, then just go ahead and have a look at some examples in the books. Test of a single variance then. Now, this isn't particularly tedious. We are going to go over a computation. So continuing with our previous example, the fund achieved 2.5% monthly return, and here was the standard deviation. Now we want to perform a test on the standard deviation. Test the hypothesis that the standard deviation is less than 5% at the 5% significance level. So here we are basically performing a test on one variance or one standard deviation. So our null hypothesis may look like this. So we could say that the null is that the volatility is greater or equal to 5%, and the alternative is that the volatility is less than 5%. Notice that we want to set this statement as our alternative hypothesis. This is kind of what we want to prove, whereas this statement here, the null statement, must contain the equal sign. So this is what we are trying to prove here as our alternative, that our standard deviation was less than 5%. Now we know that the sample standard deviation was actually 4.2%, which is lower than 5% at first glance, but is this statistically true? Now, the test that we're going to be performing is known as the chi-squared test. The formula for the chi-squared test is n-1. Again, that has to do with my degrees of freedom. Then I'm going to take the sample variance in the numerator, and I'm going to divide by the population hypothesized variance in the denominator. And that is how I'm going to compute my computed chi-squared statistic, which I'm then going to have to compare to my critical chi-squared statistic from the tables. Okay, well, continuing with the previous example, we know that 2 years of monthly data are 24 observations. We're going to lose 1 degree of freedom here. Our sample standard deviation is 4.2. Our hypothesized standard deviation is 5. So this is the formula that you need to be computing, my friends. And the answer here will be 16.23. Okay, so that is my computed chi-squared. I then need to figure out my critical chi-squared. Remember here that the wording less than signifies that this is a one-tailed test. So the entire 5% significance lies in the left rejection tail. So back to Excel then, chi-squared, okay. Well, here we'll just use the chi-squared function, dot inverse. Now it does come with two functions, .imv and .imvrt. RT is for the right tail, but we don't need a right tail here because it is a one-tail test where we are just looking at the left tail. Are we having a standard deviation that is less than 5%? Remember, I do want 5% in the left tail, so the entire rejection probability sits in the left tail. And also, I want 23 degrees of freedom. So I'm going to get a critical chi-squared value of 1309. Okay, back here, we can write that. So critical is 1309. And now we can go on the diagrams and just show that. So if I just go here, I can, obviously this isn't going to be symmetrical. Chi-squared is a squared number, so it's going to start at 0 and, it won't be symmetrical as the normal distro. But the point is that we have the critical at 1309, so that is determining our rejection tail, and our computed value was greater than that at 1623. So let's say 1623 is here, and you can see that 1623 is not in the rejection tail. Anything under 13.09 would have been rejected. However, because our computed value is above 1309 and it is not in the rejection tail, our conclusion in this case will be to fail to reject the null. Therefore, we are confirming the null here. And if you remember what the null says, is that the volatility is either equal to 5 or maybe even greater than 5, but it is not less than 5, at least with a 95% confidence level or 5% significance level. Okay, so cut a long story short, if they ask you for a test of a single variance, it's going to be the chi-squared test. Okay, and the last thing they can ask you here is test on two variances. So in this case, I'm going to compare the variance of one sample or the standard deviation of one sample to the standard deviation of another sample. This is going to be an F test. So the computed statistic for the F test is to take the larger variance, let's call that SA, in the numerator, and the smaller variance in the denominator. So that's very, very easy formula, as you can see. So let's have a look at our problem. The problem says test the hypothesis that the variance of returns for a portfolio has changed before and after a regulatory change at the 5% significance level. So we have before and after, we have standard deviations of weekly returns, and we've got number of weeks. We can see that the standard deviation before the regulatory change was greater than the standard deviation after the regulatory change. However, the wording here says has changed. It doesn't say has increased. It doesn't say has decreased. So it kind of tells me that the null hypothesis simply wants me to take the volatility before and compare it to the volatility after, i.e. this is going to be a two-tailed test, right? Are the two volatilities equal, or are the two volatilities perhaps different from each other? Okay, so we've got a two-tailed test. As you can see here, the formula will take, in our case, let's change the subscripts. In our change, we'll take the larger number, which is 2.3. So we're going to take the variance before as my numerator, and the variance after, we'll take it as the denominator. Okay, so let's go ahead and do this. So our computed F statistic is going to take 2.3. That's the volatility, so I'm going to have to square it over 2.1 squared. And that's going to give me 1.2, my friends. That's going to give me 1.2. Remember, I'm performing the test at the 5% significance, so I'm going to need an upper and a lower critical F values. Again, we can use Excel here to get those values. My lower critical F and my upper critical F. So my lower critical F is going to come from F dot inverse, and I'm doing it at the 5% level, which I'm going to have to slash into 2. So the rejection tail to the left will be 2.5%. The degrees of freedom for the F test come in pairs, so you need to provide both the degrees of freedom for the numerator as well as for the denominator. In our case, the degrees of freedom for the numerator will be so the numerator is the volatility or the variance before the regulatory change, and we have 200 weeks. We have to lose again 1 degree of freedom, so we go down to 199. The new denominator is the variance of returns after the regulatory change. Again, we are provided with 200 weeks there, so we're going to lose 1 degree of freedom there as well. And we can see that our lower critical value is 0.76, let's say. Now we can round that to 2 decimal places. And for the upper critical value, it's going to be f.inverse.right. And here I'm going to say that again, I want 2.5% in that right tail at this point. The degrees of freedom again will be 199, 199, and I'm going to get 132 again, which I can round to 2 decimal place. So spot 76 verse 132. Again, if you want to visualize that, you can. So let's have a look. Again, the F table is an asymmetrical table, but that doesn't matter. So we've got spot 76 on this side as a rejection tail. Here we've got 132. There's a rejection tail. So if you fell into any of those rejection tails, you probably need to reject. However, our computed F statistic is actually only 1.2, so it's somewhere here. And because it's not in a rejection tail, we are not going to have to reject. So what does that mean? We will fail to reject the null. So this is our null confirmed. Therefore, we will be saying that we are 95% confident that the volatility of returns of our portfolio before the regulatory change is equal to the volatility of our portfolio after the regulatory change. And that's all I had for you in the wonderful world of hypothesis testing. I hope that helped you guys. But obviously, you're going to have to hit a lot of question practice after this video. And of course, I look forward to seeing you in the next video. Goodbye.